Okay, so welcome back. Last time I was talking about Copernicus and the first serious push for a heliocentric model since Aristarchus of the ancient Greeks. And as I mentioned, Copernicus's model um, was not super accurate or anything. There's actually a pretty cool, I don't think I have it here. I think it's actually um, back in Tennessee. There was a cool compilation of uh, historical math texts. So the compilation itself was called On the Shoulder of Giants. So I will highly recommend having a look at that. Uh, Actually, as I'm going to Tennessee soon, maybe I'll grab it while I'm there to have a physical copy of it. So, on the shoulders of giants, this references a Newton quote, who says something like, "If I've seen further than most people, it's because I stood on the shoulders of giants," referring to people in the past whose work his was based on. So, On the Shoulders of Giants is the name of the compilation. It has works from Copernicus. I can't remember off the top of my head the name of the work where he first outlines the heliocentric model, so I have to think about that for a second. Galileo. Specifically, it has Galileo's dialogues concerning two chief world systems, which is actually a pretty funny dialogue between a supporter of the heliocentric model versus a supporter of the geocentric model. It's actually also the thing that got Galileo in trouble and had him under house arrest by the Inquisition until he recanted and was still under house arrest for the rest of his life. It had Kepler. I also can't remember the name of his major work where he outlined the laws of planetary motion. I want to say the first two laws of planetary motion came in one work, and the third one was added later. And Newton, the Principia Mathematica. Okay, which we're going to talk about all of these people. We're also going to talk about those works that I just mentioned. But this compilation book I highly recommend because it actually has the original works translated. So it has these works translated into English, and it's interesting to read these. So looking at Copernicus's work, again, as I said, his model wasn't great for predicting anything. The most important thing that his most important contribution was that he brought back the idea of the heliocentric model to Europe at this time, and it's from this point that it never leaves the European scientific consciousness until eventually with Kepler and Newton really nailing it down. But Kepler is the one that came up with the model that really described the motion of celestial mechanics and kind of nailed shut geocentrism forever. So his most important thing was bringing this idea into European consciousness again, and also mentioning correctly that assuming a heliocentric model of the solar system vastly simplifies a lot of what would have to be happening without that. Okay, so with the geocentric model, there's just too much stuff you have to add in. But Copernicus himself still used epicycles, still used Ptolemy's data, and so that's kind of the reason why he was doomed to not have a description that was too accurate. Okay, so I'm going to get to Kepler, but first I'm going to talk about a couple of intermediate figures. So the next is Simon Steven. So he was a Dutch mathematician. So he was born in 1548 and died in 1620. He was a big proponent of decimal fractions. In fact, he essentially created the study of decimal fractions. So this was kind of his big mathematical contribution. He's probably best known for a scientific work called Statics and Hydrostatics. So most known for statics and hydrostatics. This was published in 1586. This book discusses the triangle of forces, resolution of forces, stable and unstable equilibrium and pressure. So triangle of forces, stable and unstable equilibria. Resolution of forces. Pressure. So what is the big deal with this? Well, he was the first to advance beyond Archimedes. So Archimedes remained king of these fields until Simon Steven published this work in Statics and Hydrostatics. So first to advance past Archimedes in this respect. In the understanding of statics and hydrostatics. Okay. So that's definitely notable. You can see, this is almost 1800 years after Archimedes. So again, to really keep on hammering the point of how much time passed between each epoch. Okay. So the next name is a name, of course, that you have heard, and that's Galileo. So Galileo Galilei. So he was born in 1564 and died in 1642. So there's a lot to say about Galileo, and I'm not going to go into too much detail because you've no doubt covered him in previous classes in various contexts. So main thing I wanted to note, mathematically, something that he discovered is supposedly he was in church. And he was bored, so he used his pulse to time the oscillations of a lamp that was swinging from the church roof. And doing this, he discovered that the period of oscillation does not depend on its amplitude. Okay, so that's one mathematical innovation. Whether that is actually how he did it or whether he came about it another way, this is the story. And supposedly, this discovery is the thing that was exploited for actually constructing these pendulum clocks. Okay, so he studied like Archimedes. He studied. So Archimedes had a work on the equilibria of moving planes, I think, which was a work in basic physics. So, for instance, some basic facts about hydrostatics and centers of gravity, basically. So Galileo actually was appointed professor after basically replicating and expanding some kind of similar results in the Archimedean sense. So he also found that a falling body undergoes a uniform acceleration which is independent of its weight. This is the famous experiment that he supposedly conducted from the tower in Pisa. And so, he checked these conclusions by studying bodies sliding on inclined planes. Again, this is harkens back to Archimedes, who there were some lost works of Archimedes and some surviving works that mention similar things, but Galileo kind of put the bookend on this. This was, there's really, it's really hard to give Galileo full justice in a quick blurb, mostly focusing on his mathematical contributions, because Galileo was was important to science more generally, and he's usually called like the first modern scientist, or the father of the uh, scientific method. The father of physics. He has a lot of descriptors that he's pretty worthy of. By far, the thing that he's most famous for is astronomy. So he he was the first to apply the telescope, which was something that already existed in the time of Galileo, obviously. He was the first to use it for studying the skies, for studying the stars. And so Galileo was mostly, kind of his most celebrated achievements came through astronomy. There's probably too many to list here in a quick list, but for instance, he discovered the Galilean moons of Jupiter using his telescope. And from these discoveries, this allowed Galileo to pretty definitively say that Copernicus was onto something here with the heliocentric model, since observing these things just made it less and less likely that the Earth was the center of the universe or even the solar system. Okay, so you're probably also familiar with the story. Galileo wrote, I believe that or at least one version of this story, is that Galileo sought permission, or at least asked nicely, for a way to write on the Copernican hypothesis, as he called it. And you might say to yourself, like, what is the big deal? Why couldn't he write on the heliocentric model of the solar system? The reason was that it was official Catholic Church doctrine that the Ptolemaic model was the one that was true. Okay, and so they had taken a dogmatic position that the geocentric Ptolemaic model was the truth, and so the Copernican hypothesis was kinda sorta heretical. Okay, not that it contradicted necessarily anything in Scripture or any kind of more like fundamental belief, but because it contradicted an official stance of the Catholic Church. And at that time, that was enough for it to be deemed heretical. And so he wanted to write on the Copernican hypothesis, and I believe he sought advice on how to do this in a way that wouldn't get him, executed or at least exiled or some other unfortunate, happening occur to him. And so the advice that he got was, well, why don't you write on it, right? But you present both sides, right? So you present both sides, arguments for the heliocentric model and arguments against it. And so he did that, but of course, so this is the result of this is called Dialogue Concerning Two Chief World Systems. I believe this is rough. It may not be the exact wording of the title. But it was written as a dialogue, a back and forth between two characters. And the character that was meant to represent not the Copernican model. The character that was meant to represent the Ptolemaic model was named Simplicio, right? Simple, and basically lost the arguments at every turn in this dialogue. So I highly recommend reading it. It's actually pretty good, and it's actually funny too. But yeah, I highly recommend reading this. But this is the thing that got him into trouble, because when he wrote this, the Pope at the time actually took it personally that Galileo was using this character named Stupid basically as a stand-in for the Pope and his support of the Ptolemaic worldview. And so this caused Galileo to be, put under arrest and put under the Inquisition, where he was, forced to recant. Where this is the famous scene where supposedly he said under his breath that, and yet it moves. He was forced to recant, and he spent the rest of his days under house arrest for daring to say that the Copernican hypothesis was probably the true one. So yeah, he spent like almost the last decade basically under house arrest. Okay, so moving on, the guy who kind of nailed shut the case on the Copernican hypothesis, Johann Kepler. Okay, and you can't talk about Kepler without mentioning as a sub topic Tycho Brahe. So Tycho Brahe lived from 1546 to 1601. Okay, so Kepler, he studied in both Germany and Austria. He was German. He was an early adopter of the Copernican viewpoint. You'll notice that he was a contemporary of Galileo. In fact, Galileo died after Kepler. And this leads to some interesting interactions where Kepler was right, and Kepler was very right, but a lot of his a lot of Kepler's work wasn't fully absorbed until later. It wasn't fully appreciated until decades after his death. But he was an early adopter of the Copernican worldview. He did some early work on theoretical models and of the solar system, and most of it was. Some of it was interesting because it was basically a Pythagorean take on the solar system, where he tried to match the Platonic solids to the solar system intervals between planets, because he's like, I have 5 Platonic solids and I have 5 of these gaps to match, and he more or less made them fit, coming up with various reasons. The name of this work is called Cosmic Mystery. And it is basically some kind of weird neo-Pythagorean take on astronomy that was not at all based on any kind of data whatsoever. So it's pretty funny that that Kepler would eventually come to the right answer in this way. So when that didn't work, he didn't give up all hope. So he kept going, and his main thing that he had going for him was he correctly noted that he needed better data to work with if he was going to try to come up with any kind of model that actually worked. And so this is where Tycho Brahe came in. So Tycho Brahe did not use telescope. He was responsible for naked eye observational astronomical data, and it was meticulously collected observational data, like I said, without the use of a telescope. He had compiled this massive amount of data, and Kepler wanted access to it. So Tycho Brahe had his own kind of strange blend of the Copernican view together with geocentrism that he believed would ultimately be the right thing, and that was one of the things he came to this conclusion through collecting this data. And he was he guarded his data very very zealously, but it turns out that Kepler went and became an assistant to Brahe. Tycho Brahe died, and Kepler inherited his data more or less. And it was this data, this amazing, it was the best astronomical data that existed in the world at that time. And it was certainly miles and miles ahead of the old Ptolemaic data, which was pretty inaccurate. So Kepler had access to this data, which allowed him to make some hypotheses based on this data and finally get a model that actually described what was seen. Right. So there were various quirks in the solar system with what the apparent motion of the heavenly bodies do. So it's not that easy to describe. It's impossible to describe with the geocentric model. But the thing is that there were these various quirks that were very hard to account for. And Kepler ultimately did this using Brahe's great data. One quick story about Tycho Brahe. He had a fake nose. He had a fake nose because he lost the tip of his nose in a duel. He and a mathematician friend of his were very drunk at a party, and they started arguing over who the best mathematician was. And they got into a fight, and they challenged each other to a duel, and they were fighting with swords drunkenly, and it ended up with Tycho getting his nose cut off. So he had a false gold or silver or brass nose, and he was kind of a party-holic kind of guy. He loved going to parties, and he loved hanging out with people and having a good time, and so much so that he was at a party having a great time, and presumably he was having such a good time that he didn't want to actually leave what he was doing, and so he needed to go to the bathroom. He needed to urinate, but he's like, I'm having too much fun to do that, so I'm not gonna leave my buddies and go to the bathroom. I'm just gonna stay, right? And so he did, and he kept staying and kept partying until his bladder burst and he died. So I guess he died doing what he loved, but that's how Tycho Brahe died, and that's how Kepler came to inherit his data. So this led to Kepler. So with Brahe's data, Kepler formulated what would be called Kepler's laws of planetary motion. So there were three of them. The first two came about first. The last one took an additional 10 years, I believe, for Kepler to formulate. So the first one is each planet describes an ellipse with the sun at one focus. What's ironic about this is, one, an ellipse is it's simpler than an epicycle. Epicycles are ridiculously complicated curves, or can be. Ellipses are simple curves, and they've been known since antiquity, right? So the conics have been known to the Greeks, or had been known to the Greeks for over 2,300 years. Apollonius, essentially wrote all that there was to write on the conics until Descartes founded analytic geometry. So the conics were, and especially the ellipse, was relatively well understood. So the Greeks already had the machinery to describe the trajectories of the planets. And it's funny that they spent so long, having these epicycles floating around, considering that it was a much nastier description, right, of what was going on. And it turned out really what was needed was just this very, very accurate data. that Brahe had access to, or had compiled himself. Um, the next is the line joining the sun to the planet. Sweeps out equal areas in equal times. Sweeps out, bounded by the ellipse. Equal areas in equal times. So these were the first two. The last one took a little bit more effort. The square of the period of revolution of each planet right, i.e. its year, is proportional to the cube of the major axis of its orbit. Okay. So this one, so this last one was stated in 1619. These first two were stated in 1609. So it was these three laws that Newton derived from his law of universal gravitation, and this was basically the aha moment that this was the right path. Okay. Well, I mean, for both things, right? For both Newton and Kepler, but specifically this, you can say that this confirmed Newton's theory of universal gravitation, or that Newton confirmed Kepler's laws of planetary motion. But this was certainly nice evidence that that we were on the right path. So as I mentioned previously, as Kepler kind of stopped contributing, as his life kind of faded out, he supported himself with horoscopes, basically, so astrology. And it was he that said this famous quote that astrology is like the daughter of astronomy, and the daughter's got to support the mother. And what he meant by that was that, astrology pays the bills, even if it's, totally made up. It pays the bills, so he was happy to do it. Supposedly, he had enough pull that so he settled in Prague, I believe, and he had enough pull in Prague that when some neighbors who were jealous of he and his family, they accused his mother of witchcraft, which was not, that's not like an idle threat in those days. That was pretty serious. He managed to get the charges dropped, so he had enough pull by then to at least be able to escape, or have his mother escape unscathed from such accusations. Anyway, so that kind of brings us out of the Renaissance and into kind of the first wave of 17th century activity, although it's a little bit of a misnomer to call it that. I'm going to cover it in this way because this is how our textbook does it, but basically we're going to discuss a wave of 17th century French mathematicians, and then more broadly just 17th century mathematics in Europe more generally. So the first stop is the 17th century in France. So we have a list of some big names that we're going to talk about in order. So the first is Marin Marsan. So he was born in 1588 and died in 1648. You may have seen his name before. Actually, near the beginning of the course, we talked about something that he did. There's Gerard Desargues. He was born in 1591 and died in 1661. There's Descartes. So he was born in 1596 and died in 1650. There was Fermat. He was born in 1601 and died in 1665. And the last French mathematician I'll mention in this little block is Pascal. Okay, so 1623 to 1662. Okay, so that's the big five I'm going to talk about in this little block. All right. So Marsan is most known for the primes that are named after him. So this was the main thing that it's known that he instigated study into. So what are Marsan primes? They are primes of the form 2 to the n minus 1. Okay. So these primes, of course, 2 to the n minus 1 is not always prime, but when it is, this is called a Mersenne prime. And this, I think I might have mentioned this when we first talked about prime numbers early on, when we first mentioned Mersenne primes, is that these primes are an exponential thing, right? It's 2 to some power minus 1. So they're an exponential quantity. And of course we know that exponential things grow fast. And so these primes, if you find that one of these things is prime for some large value of n, this is going to be a ridiculously huge number. And I want to say that basically at any given time in the last 50 years, the largest known prime is typically a Mersenne prime. And that, again, is just because the way that it's defined, it's an exponential thing. So it's not surprising that this would typically be one of the largest known primes, or something of this form, I mean. So one thing that's neat about him is that he didn't contribute much more to math, but he corresponded with all of the rest of this list. Okay, so in a sense, he kind of kept in touch with everyone and basically, kept information flowing. So that's another contribution. It's kind of a secondary contribution, something maybe you don't think of that often in things like this. Okay, so Desargues is sometimes called the father of projective geometry. Maybe I'll even say that here, but I'm going to add a little this little subtitle here. So he's called the father of projective geometry, namely because the most important thing that he did was prove what's called Desargues' theorem. I should mention, though, that I've said these words previously, right? Even though Pappus proved the first projective geometry theorem, right? So in a sense, Pappus is really the first person to deal with projective geometry. So in a sense, Pappus is the father of projective geometry. But Desargues showed Desargues' theorem, which is another theorem in projective geometry, similar to Pappus's theorem, and they are related to very specific things. So so what is projective geometry? I'm going to relegate a lot of comments on projective geometry to links that I put in the info dump, and I may go into more depth about this stuff as the course progresses. Once we get to the 18th century, may start talking more about projective geometry. I've mentioned projective geometry before. One way to think about it is, one, it is the geometry that arose out of considerations of perspective. So actually, some of the earlier practitioners of projective geometry weren't mathematicians like Desargues. So Desargues was working in the 1600s, right? But there were Italian artists in the 1400s that were doing projective geometry through their art. They just didn't technically know that that's what they were doing. So the mathematics of perspective is essentially part of projective geometry. Another way of thinking about projective geometry, if you think about Euclidean geometry being the things that can be constructed with compass and straight edge, projective geometry is what can be constructed with only straight edge. Okay. So it seems like it's a much more primitive thing than Euclidean geometry, but in a sense, projective geometry is kind of the thing that unifies all of geometry. And a lot of geometry kind of sits inside projective geometry. And so it's important for various reasons. So in fact, Desargues' theorem is essentially a theorem about perspectivity. It's about being in perspective. So he proved Desargues' theorem, which is, as I said, the second theorem ever proven in projective geometry. So what does it say? Okay. If two triangles in the same plane are not, are so situated that lines joining pairs of corresponding vertices are concurrent I'm gonna toss in something here, if only at infinity, as a possibility, and I'm going to talk about what I mean by at infinity. Then the points of intersection of pairs of corresponding sides are collinear, if only on the line at infinity. And conversely. Now, this is the way that Desargues worded it, but what is he actually saying? So I'm going to look at what's called the parallel case. So here's the setting. What is the statement? The statement is that I have two triangles set up in this way. Okay, so when I connect the vertices, all right, the corresponding vertices of these triangles, they meet at a point O. Then, if AB and A prime B prime are parallel, and if AC and A prime C prime are parallel, then BC and B prime C prime are parallel. That's one statement of Desargues' theorem. Look at these triangles. Imagine that this O is your eye, and you're viewing these triangles. So these lines represent your view lines. What is going on here? These two triangles are said to be in perspective. So the two triangles are said to be in perspective in that picture. So in the picture, the two triangles are in perspective. Now, there's some confusing stuff here that will require a little bit of an aside. So one, in perspective, that's me mentioning, the notion of perspective as it pertains to like art. Okay, but what's the idea here? Okay, so, and what's this notion of at infinity and on the line at infinity? What's going on there? Okay, so here is my idea. Okay. Imagine that you are given the task, right, of drawing an image, and the image is supposed to be a point of view image where I'm standing in the middle of, say, some railroad tracks, and I'm looking at one end, right? And there's no trees, there's no obstacles in the way, no mountains, no hills, no nothing like that. So I'm on a completely flat area, and I'm just looking in the direction of the train tracks, and I'm standing right in the middle of them. What would that look like from my point of view? Well, the train tracks would... Here's a question, right? If here is my horizon... Right, so here's my horizon. What do the train tracks look like? If I'm standing here, right, well, I'm looking here, right? What would my train tracks look like? Would they look like this? No, of course not. Right, what is this? What is this? This doesn't look like anything. If I'm looking toward the horizon, train tracks don't look like that. Right, what do train tracks look like if I'm looking off toward the horizon? So here's my horizon line, and I'm looking toward the horizon. What do my train tracks look like? They look more like that. Huh. Now, you look at this and you say, well, this is a little weird, because you know in your mind that train tracks are parallel, right? Well, I just drew two lines that are very much not parallel. You say these lines meet. They meet here. Okay. Well, but which of these pictures looks more like me standing in the middle of railroad tracks looking off toward the horizon? Well, clearly this one, right? This looks better than that. This doesn't look like anything. I don't even know what that looks like. But this actually does look like me standing on some train tracks or a road or something, and it going off toward this horizon line. So what's weird, right, is that they look parallel. Right? There's the notion of they look parallel. They're clearly not. If this is a Euclidean figure, here's a line, here's two lines, they definitely intersect, right? So in Euclidean geometry, these things intersect, right? But what about the geometry of how they look, right? This is projective geometry. And so what we would say is that this horizon line represents a line at infinity. It's off. Okay, and these two lines, they intersect at infinity. They intersect off in the distance, right? At some unattainable place on the horizon, right? They don't actually ever intersect, right? They intersect off at infinity. Okay, and so this is this notion of what looks parallel or what looks to be the same size, right? So for instance, a tiled floor is one of the earliest examples of perspective. Is draw a tiled floor, and maybe I'll even do that. I'll show you an example of how you can draw a tiled floor using only a straight edge. That's all you need. So using straight edge only, you can draw a perspective view of a tiled floor that actually looks like all the tiles are the same size. Now, if you take out a ruler and you start measuring them, you're going to clearly see that they're not the same size, but they look like they're the same size. Right? This is the notion of perspective, and this is key in projective geometry. And so an example of that is exactly this picture of Desargues' theorem, which is two triangles in perspective in this way. Okay. Now, it turns out that Desargues' theorem is true and can be proven only with postulates 1 through 5 of Euclidean geometry. Okay. So Hilbert showed this. It turns out that Desargues' theorem is fundamentally related to basic algebraic things in Euclidean geometry. Desargues' theorem allows you to define multiplication, and in the context of multiplication, it is what gives you, ignoring the Archimedean principle, as it's called, Desargues' theorem gives you associativity of multiplication. So Hilbert was the first to notice this. Hilbert being the same guy that came up with this way of coming up with a completely logically consistent form of Euclidean geometry. He's the same Hilbert that Hilbert's axioms are named after. Pappus's theorem is exactly associated with commutativity of multiplication. So both of these facts are due to Hilbert. Okay. So both Desargues and Pappus's theorems can be shown in Euclidean geometry using just postulates 1 through 5. Okay. Doesn't depend on anything else that you're assuming in Euclidean geometry. All right. Okay. So, maybe I should stop for now, I think, before I get into Descartes, because that will take a little bit longer. Yeah, I think that's more or less all I wanted to say for today. So next time we'll talk about Descartes, and we'll finish up with the 17th century French mathematicians for the most part, very quickly moving toward some names that you're very familiar with, like Newton and Leibniz. Once we progress past Newton and Leibniz, we'll be going through the 1700s. Once we get to the 1800s, it will be time to make some decisions on how the course unfolds. So I will let you all know about that. What I plan on doing is basically sending out a kind of poll to see what direction you want the course to go in from that point. Because once we get to the 1800s, the specialization kicks into overdrive, and it becomes impossible to kind of cover math on all fronts. So up until the 1800s, we will basically be able to progress uniformly, covering basically all frontiers of mathematics as it develops. Once we get to the 1800s, it becomes far too complicated to do that. We would never be able to keep up. And so that's where there will be a choice to be made. So anyway, I will let you know about that as it comes up. So I believe that's all I wanted to say for today. So I will see you all next time.